So, welcome everyone. First, I'd like to thank the organizers, Sujata, and the others who made it possible for us all to be here today. So, the topic of how to visualize neural network parameters and activities is relevant for many of us who are developing models in deep learning, or if you're going in the more research direction and you want to be able to come up with something new, find something that will enable other investigators or end users to benefit from getting intuition into the process. First off, can everyone hear me clearly in the back? Okay, great. All right, so about me. So I originally was working in neuroscience research in the University of Texas at San Antonio, and I was interested in the brain and the activity of the brain, looking at brain activations. And currently I'm a master's student in cognitive science at the University of Osnabrück in Germany, where I'm working a bit in the math department, making some visualizations with D3JS, and writing my thesis with a company called Pelterion in Stockholm. It's an AI software company. Another thing, I'm working with Intel as an AI software innovator, and I can tell you a bit more about that later if you're interested. They basically support early prototyping and using their software and hardware. And at the end, I'll have some gifts for you, courtesy of Intel. And I was able to bring some things for you guys to have. I'll tell you at the end. So first question might be, why is this relevant to us to understand, to get intuition about deep neural networks? If the predictions are useful, that might be enough for our boss, or a boss might be happy with that. On the other hand, there's other people who are very interested in understanding and explaining why. So the second keynote topic was very relevant. The interpretability of networks and models is essential for many people in society. So specifically, I'll introduce two projects that are very relevant. Jason Yosinski's Deep Visualization Toolbox, which is useful for visualizing neural network activation for convolutional neural networks, as well as Karpathy's text-based visualizations for recurrent neural networks. And TensorFlow's TensorBoard, which many of us who use TensorFlow have found useful, and other notable projects, and a summary. So why is it relevant to understand and get intuition about the activity of these neural networks? One part I happen to be biased about is the desire to really understand what's happening. So especially if you're working with natural models, and you're trying to make a prediction about why is this part of the brain being active rather than another in a certain task, you want to be able to not only make a prediction, but also to explain and understand what's happening. So there's an example given by Noam Chomsky that a camera pointed out of a window can make better predictions than any physicist could about what's going to happen next. But it doesn't give insight into the underlying principles. So those are the principles that we're after if we're interested in science. Deep learning, so for end users, it's also relevant to be able to explain and interpret. So whether it's a self-driving car that has to make a decision in one case, or if it's a financial model that you're trying to analyze, it's going to be useful for end users to be able to understand why certain predictions were made. Also for model developers who go down the path of having to build models, they'll benefit from every intuition that they can get. And also, increasing performance overall depends on having an understanding about the mechanisms in neural networks itself. There's a quote from Feynman, which I happen to find inspiring. He says, "What I cannot create, I do not understand." And I think now, because we have so much power to create with these tools, it brings us to the question of saying, well, if we can't explain it, we probably also don't understand it as well. So introducing convolutional neural networks. So convolutional neural networks are commonly associated with image detection, and it works basically by taking an input image and convolve a filter kernel across the image and create a feature map. So like this, in this case, we can see a convolutional filter with convolved over the input image to create emboss feature map. So basically, at low levels, it works like an edge detector. Sorry, edge detector would, and the deep visualization toolbox is really useful because it lets you visualize several different types of features, both at low levels and high levels. You can download it and play with it in Python at Yosinski's repository in GitHub. And he's running AlexNet in Cafe. And I'm going to break the rule about no live demos, give you a quick live demo because it's beautiful. And gives you a lot of intuition really quick. So here we see the deep visualization toolbox. And this is the AlexNet running in Cafe. And these are the various, from left to right, the various layers of the network. So first convolutional layer, pooling layer, normalization layer, then onward until the end you get to the fully connected layers. And it tells us on the left, so this is an input image, and it tells us the classification. So this is using ImageNet, I believe, yes. And we can see for various images what the classification is. So at the first layers, our filters are pretty basic. On the right, we see in these the 9 squares here. These are images from the training data that are producing the most activation for each of these given units. So each of these squares is a unit within the layer. And the top and bottom are images generated to produce the most activation. Also, let me show you. So let's go back to the. So here's a visualization of images that were generated to produce the most activation in the layer. Okay, so we can turn on the camera, the webcam, and we can get a live preview of how that works. There's a fairly pale white guy in front of you. If we show you, so given this convolutional filter, we can see that the activation will be corresponding to edges on the left side. So this will show how this unit is activated based on that filter. And then on the unit to the right shows the activation of edges on the other side. So at low level, you get low level features such as edges, colors, and the convolutional network uses these and builds on them to produce a final classification. It gets quite interesting at higher levels. At the higher layers you get to, in the 5th convolutional layer, you can see there's one neuron that lights up in the it detects faces. So there's even though this neural network was designed to the model was designed to classify images, so people versus animals versus school buses, there's a face detector embedded within it. So what's interesting about that is there could be a lot of other features that could be extracted from ImageNet, for example, from models that are trained for higher level purposes. Lower level features could be found that are embedded within. So, and here are the images that that this neuron was most important for producing the final classification for. And here are the parts of the images, the parts of these images which were most relevant to the classification. So if you either obscure these parts of the image, it would either classify differently, or if you perturb it. Okay. And it's also possible to see with this tool relationships between layers. So how do lower layers relate to higher layer activations? So that's really neat. If you want to see your face light up on a neural network, come by afterwards. We can check it out. Okay. And another important neural network useful for visualizing is recurrent neural networks. So with the recurrent neural network, one can see the relationship between sequences that are a model that's trained on sequences, and to see visually how relevant certain parts of that the data corresponds to the output. So in a recurrent neural network, you have input fed into a hidden layer. A hidden layer which depends both on the current state and also on the previous state of the network. And that then produces a output. So an output classification, prediction, generating text, so forth. And so an example of how that works, so if your sequence is hello, a word hello, there's 4 unique characters in hello. So you would need a one-hot encoding for 4 entries. And each letter would correspond with the corresponding element. So H would be the first, second, E would be the second, L would be the third. And if you were trying to predict the 5th letter in this sequence, you would want it to predict O as the 5th letter. And the way that roughly works is you have an input layer and matrix multiplication to the hidden layer, which then also is an activation function is applied and produces an output layer. Then at further time steps, you have the hidden layer being affected by both the new input that's coming in and also by the previous hidden layer. So the hidden layer represents a kind of embedding of it's a hidden layer. It's an embedding that's useful for storing memory from previous learnings. And so carrying the memory forward in terms of an activation function applied to the weight matrix times the input, plus a transition matrix times the previous time state hidden layer. So visualizing that was pretty clever from Karpathy. He looked into the cells of the LSTM, and kind of like if you were looking into a brain, and if you were to find that a certain part of the brain was active whenever you were talking with your friend versus when you were talking, another part active when you talk with your coworkers. So he found that there are certain cells that activate, for example, when you're approaching the end of a line. So there's a part of the LSTM, even though it wasn't trained specifically for that, it learns this along the way. Also, you can visualize with text. There's cells that turn on only within inside quotes. So it's clear here that there's some context that's being learned, and even though it's understood if you're generating text with an RNN, that there's also features that are going to be learned and incorporated into producing accurate text. Karpathy also trained on cells that activate only within if statements. So it's pretty useful to think about that, or it may be interesting to consider that syntax and semantics, context are things that we've defined heuristically. There might be further analytical explanations that we're not aware of. We could discover through these kinds of methods. TensorFlow also has another feature called TensorBoard that's useful for visualizing weight histograms, for example. Also doing embedding visualizations. So if you have word-to-vec embeddings, you can see them in 2D or 3D. You just have to attach to the summaries to make sure that it saves whatever it's, it saves those weights. And also the graph visualization, which is useful when you're designing your model, or if you're finding that your model's not learning, or if there's a bug. It's quite useful because, for example, you can see that the color encoding for layers will be the same if the hyperparameters are the same. So if you find that there's a bug, something's not working, you can check this and make sure that there isn't, for example, 2 convolutional layers, that one has a slightly different setting. If so, they would have different colors. It's useful for debugging. Also, embedding visualizations with PCA and TSNE. We can take a look at that later if you like. And the playground. So this is more for getting general intuition about how neural networks work. So if you want to see how does, for example, information move from one layer of the network to another, how does the model depth affect the performance? This is really useful for explaining that. And this past year, TensorBoard added a new ability to add extensions. So recently we saw a handwriting recognition plugin that can do live handwriting prediction, and it will basically learn the style of a person's handwriting. So the ability to customize visualizations for specific projects provides a lot of opportunities. So if you're working on a project for a long time and you want to develop a consistent visualization, you can share that with the open source community through TensorFlow. And heatmapping.org has some other very nice visualizations. I'd like to open up and share with you as well. So here we can see the MNIST predictions, and it will predict from the input. It'll show which parts of the input are most relevant to the classification using, they call layer-wise relevance propagation, LRP, and there's a toolbox with available on GitHub. So you make a nice pretty one, more or less, and it predicts it correctly, and it shows you which parts of the input were most relevant. So it's useful to play with to get an intuition. Also, a cafe model shows you which parts of the image input are important for the classification. And then even it predicts tabby cat. And the text one as well. So given input text, lets you classify and explain it. So if we went to the second keynote, we heard about other projects like Lime and ELI5, which do roughly the same thing. Okay. So other notable projects include the University of Osnabrück. A colleague of mine here is helping to develop a platform. It's a PyQt visualization that'll take any neural network model, whether it's in Caffe, Torch, TensorFlow, so forth, and to be able to visualize live the unit activations. It's very early in development stage, so we started about a month ago. But you can check out the GitHub, make a pull request. And also some other useful, there's a useful article, how to use TSNE effectively. So TSNE is so useful for visualizing the embeddings or to visualize the data distribution, high-dimensional data. So an example here, I created a genre music melody generator using Magenta, and I wanted to see what the distance was between different music genres. So if a music was encoded with both classical and metal, but compare that to musics that were encoded with both classical and rap, for example. And through that you can find what is the distance between genres. And so here it was possible to see, for example, that classical over here is quite separate from, say, country over here. So TSNE picked up on that pretty well, whereas PCA probably would take some more finessing to get it useful. ELI5 and Lime were explained earlier. And so to summarize, you can explore neural network features much more easily if they're visualizable, or if you can kind of take them out of their context and put them into a tool that gives people insight. And there's also a possibility of discovering these latent codings, latent features that were not otherwise intuitive or visible. And so deep learning has a lot of promise for that. Creating tools to help guide scientists find the right model, because it's not obvious which models to pick until someone has already tested it and compared it to other models. So it's one of our hopes that we'll be able to create a higher level API for that. And also this scientific research has high social impact, as Christine mentioned in the keynote, that not only will the law start requiring certain interpretability factors to be present, but it also is useful for the end user to know what's guiding them. So we have some image sources, and yeah, a couple of screens were taken from some useful TensorFlow YouTube video, and also Yosinski's YouTube video, which was helpful. And a little plug, if you're interested in Intel's machine learning and deep learning webinars, they have some link, you can check that out here. And so we were able to get some free Amazon vouchers for you if you create a project through the Europe's DevMesh for Intel. It's a place for sharing projects and collaborating. So they said about €50 voucher, so I recommend checking it out. All right, thanks a lot for your time. Any questions?
Any questions?
Could you show an example of the CNN visualization with a misclassified example?
Yes, CNN visualization with the misclassified example. So in the deep visualization toolbox, for example, or generally?
You showed the orangutan and it was obviously an orangutan.
Yes.
What happens
Sure. It's actually the most common misclassification that I've seen is where you try to have it classify you as a person, and it almost always fails. So it's detected me as everything from like a teapot to a bow tie. So I think it's not like robust against that kind of thing. I'll be happy to show you afterwards. If anyone wants more hands-on demo, wants to see their face light up on a network, you got to do it yourself to really get the experience. Okay.
Okay. Thank you very much.
Thank you.